Thank you, Zoom. All right, so very briefly, in case you haven't heard of us, Boston Dynamics, we're located in Waltham, Massachusetts, and Mountain View, California. We have 3 robot projects that are active right now. Spot, which is focused on things like inspection, sensing, and manipulation, which you can go to our store right now and buy if you want. Stretch, which is focused on logistics, so unloading boxes, moving things around in the real world. And Atlas, which is focused on research and development, creating new technologies, and feeding them out to the rest of the company. And honestly, focused on getting people excited about robotics, which is the part I'm most interested in. This is Atlas. So Atlas is a hydraulically powered humanoid robot. It's designed to be approximately human scale and approximately human strength. So it's about 1.5 meters tall, weighs about 90 kilograms. All of the actuation is hydraulic. We have our own custom hydraulic power unit, our own direct drive valves, custom battery to power the whole system. All the computation is on board. We have 3 pretty standard high-speed desktop CPUs. We use time-of-flight depth sensing to sense the world, and some force sensing. I love working on Atlas because it is a pretty physically robust system. We do a lot of crazy things with this robot, and I believe in all of these cases, the robot just got back up and did it again. That's not to say it's indestructible. We break the robot all the time. We have the best technicians in the world who fix it when we do so. And so having a robot that is robust enough that we can trust it to do crazy things like this means that we can really push the boundaries of what it means to be an athletic humanoid robot. And so we can do things like vaulting and jumping and spinning and flipping and do them over and over and over until we get them right. So our mission on Atlas is to create breakthroughs in dynamic control, and we want to meet human performance and eventually exceed human performance. And I think we've met that goal in some places. There are things the robot can do that I cannot do, but currently there aren't any things the robot can do that no human can do. So we still have a long way to go. We're focused on parkour and dance because they really push the boundaries of what's possible with a humanoid robot, and because they are really easy for humans to relate to. They're very exciting activities. And I think that helps sort of motivate us and focus our work and help with getting all of you excited about robotics. The core technologies on the control and perception side, we focus a lot on rapid behavior authoring. So creating new behaviors for Atlas quickly, testing them, iterating on them, and making actually work on the robot. We focus on perception, so how do we take those behaviors and map them into the real world and actually achieve them on the robot. All of our control that I'm going to talk about today is powered by model predictive control. We do tons of MPC, various flavors. We'll talk a little bit about what we do and what's coming up next. And we rely on hydraulic actuation to let us do extremely high power things over and over and over. So when we're creating behaviors for Atlas, we've traditionally done a lot of work on trajectory optimization. And what this looks like is an engineer writes down some specification of the trajectory, which might include something like the mode sequence, so flat foot, toe, flight, land, and some general hints about what you want it to achieve, like achieve a large z angular momentum and land with a rotation of 2 pi. That gives you a 360 jump. When we actually turn that onto the robot, it's not sufficient to have a good trajectory result. No matter how good your trajectory is, you still need some way to stabilize it on the robot, or the robot will fall over because the robot is not the model. So we use model predictive control, telling the controller to stay as close as possible to the desired trajectory while maintaining balance and staying within the feasible limits of the robot. That offline optimization, we rely on a separation between the centroidal and kinematic parts of the robot. This is a pretty common technique. I've got a few citations here. This is work that has been done pretty thoroughly by a lot of different people. But we solve for a single optimization for the centroidal dynamics, treating the robot as a potato that can change geometry, so shaping its inertia slightly. And then we solve a kinematic optimization to choose a sequence of joint angles that are consistent with that. And the result is that we get reasonably dynamically consistent behaviors. Never perfect. We rely on the controller to sort of fill in the gaps and actually make things work. Online, we actually do something pretty similar. So we run model predictive control over the centroidal dynamics, and also sometimes over the robot's full kinematics. We have a couple of different flavors of this. Sometimes we're doing single shot IK. In the most complicated version, we're actually solving kinematic and centroidal MPC at the same time in a single optimization. The time scale is really the big difference here. We actually have to do this at speed inside the control loop, so we can't spend minutes optimizing the trajectory. We have milliseconds to do it. So how do we do that? We rely very heavily on the nonlinear dynamics of the system. So we're not dealing with purely linear models. We're always dealing with nonlinearities. And we deal with that by linearizing around the best guess we have for the solution, solving and iterating on that. We compute contact wrenches in MPC, locations of contact, timing adjustment, which is very important, and in later versions also the joint configurations. And we rely very heavily on the natural sparse structure of these problems to accelerate them. So things like knowing that the dynamics only depend on the velocity at a particular point in time. So trajectory optimization worked really well for designing 360 jumps, pose jumps, happy jumps, all sorts of things. When we were asked to start thinking about dance, it really doesn't work well. If you ask an engineer to write down a trajectory optimization problem whose answer is this, I don't think it's possible. You could, if you were to specify exactly the sequence of joint angles, but as an engineer, we're not very good at that. And there's a lot of sort of style in dance that's not well captured by a quadratic cost on center of mass. So we actually turned to the world of animation. So we have a pipeline where we take an inspiration video like this and actually hand it to a real professional animator using animation software. And they produce a sequence of joint angles mapped to the robot. And the difference between this and an optimization is that the animator is, in some sense, an artist who can actually capture some of the stylistic parts of the dance while also trying to stay within the physical limits of the robot. Now, again, no matter how good that animation is, it's still never going to play back perfectly on the robot. The robot is not out. But it turns out that the same kind of model predictive control that we use to track optimized trajectories works very well for dance. And so we actually run exactly the same MVC, where we can take inputs from trajectory optimizations and run them, or we can take inputs in the form of animations and run them on the same robot. And so we can create pretty good matches between the robot's actual behavior and the original stylistic inspiration. And so what that looks like when we put it all together is something like our recent dance video. So in this video, you're actually seeing sequences of behaviors, some of which are purely trajectory optimization, some of which are purely animation, and some of which are actually animations that were then refined through trajectory optimization to come closer to the robot's capabilities. But we're running the same MVC controller at all times, and it's just sort of blending between them as we go. So we have a bunch of behaviors, but everything I've shown you so far is on flat ground, and therefore has no perception involved. So how do we take these behaviors and map them onto a world that is not perfectly flat? So Atlas has a time of flight sensor. We use that to get point clouds, so 3D representations of the space around us. And we do a lot of work fitting geometric primitives to those point clouds, and then turning those primitives into targets. Jump here, vault here, back from here. What that looks like is this. So we showed this in our perception for parkour video. This is the robot live running the run that was actually in our YouTube video, and we're showing in green the geometric primitives that we fit, and in white some of the plane detections that we're using to inform those fits. And so from those perception targets, we're creating targets where we ask the robot to jump and where we ask it to land. Okay, but I've talked a lot about trajectory optimization and animation. Those don't map directly all that well to when you start trying to drive things with perception. It would be completely infeasible to develop a library of trajectories that consist of every possible amount of translation you might be asked to produce from a perception system. The boxes will never be exactly where you were expecting them. The robot will never be exactly where you expected it relative to those environments. And so we rely a lot on trajectory warping. So taking, for example, a trajectory that might jump up onto the red box and just naively stretching it a little bit so that it could jump up onto a taller box. That doesn't actually produce something dynamically consistent. You can't take a ballistic trajectory and do some naive warping and get a new ballistically consistent trajectory. But the key insight is that it doesn't matter. All we're doing is providing sort of a best guess to MVC. MVC knows the real dynamics of the system, and so it can adapt to a trajectory that is not actually physically feasible. And so what I'm showing here is some early work we did when we were doing perception parkour. So we're taking a couple of template jumps and stretching them to different amounts of translation and forward direction and up and down to adapt to the various boxes that the perception system is seeing. Okay, so everything works great and it's all fine, right? So there are a lot of things that we found that don't yet work well or that are still opportunities for us to improve. I think that our dance video showed a lot of whole body coordination, but not as much as it could have. I think there's more we can do when the robot, sort of every motion of every limb is heavily impacting the overall dynamics of the robot. Basically, I want to dance like BTS. We have trouble in the controller you see here with improvisation. So things go badly on the robot a lot. And the controllers that we've shown so far tend to not do all that well as soon as they get sort of away from the reference that we're asking them to track. And so I want to do better on that. How can we improve our ability to move away from needing very clear trajectory inputs? Robot was fine. Another question is sort of how do we think about performance limiting behaviors? So how do we handle things like the vault? The vault was really the hardest part, I think, of the parkour challenge because it's at the absolute limits of the robot's arm torques and arm kinematics. And as a result, it was very difficult to make that reliable. So how do we write controllers that can better handle situations at the robot's absolute physical limits? And then finally, I've talked a lot about designing sort of very clear trajectory inputs or clear animation inputs. But what if you just want the robot to put its hand somewhere? It seems ridiculous to generate a trajectory optimization offline to move the hand to somewhere. And so we don't want to do that. We want to be able to tell it, just put your hand here, but do it in a framework that is consistent with doing backflips and lifting things and throwing things, and sort of carries all of the full benefits of this highly dynamic NPC. Okay, so one of the important tools there is actually putting kinematics directly into NPC. So all the work I've shown you so far has involved a centroidal model predictive controller, and then a single shot IK to sort of help us map our joints to the result of that centroidal optimization. And that's what I'm showing in the bottom left here. The new cool stuff is, what if we just ran NPC over the robot's full kinematics? It turns out you can do this. So this is the robot simultaneously solving an NPC over the centroidal dynamics and the full kinematics to do a jog over some terrain and to hop. And here it is on the real robot. So this is a quarter speed jump. The robot is showing you in the bottom left where it's planning to be in the future. That's the solution of the NPC problem. And it's actually working. Okay, that's great. I mean, we can jump. We could already jump before. So what can we do that's new? Well, one thing we can do is now we can dance a little bit more like BTS, and we can do it at a much faster pace. So our previous dance effort took sort of a multi-month process of iterating on behaviors, mapping them to the abilities of the controller. We were asked to do this dance, and in 2 days we went from an animation concept to something that we were able to ship off to a filming company and film. And so now we're not quite there. I think the lack of a head really impacts our ability to be quite as cool. But I think we're pretty close. And having a controller that is more aware of the full robot kinematics really makes this kind of thing much easier to do. Okay, I talked about making NPC taskable. Can we allow the Atlas robot to do things that we haven't created trajectories for? So here's some video fresh off the press. We're going to run up and we're going to pick up this thing. This is a 25 kilogram weight. We have no trajectories in our library that know anything about weights or lifting or bending. We're just telling the robot, hey, put your hands here and then expect some force. So that's a 55-pound barbell. That's a pretty heavy thing. It's challenging to lift that straight off the floor. Here's what the robot is thinking about as it does that. So we're taking point cloud data, as you saw in the pro video, creating step targets. And this is showing you the solution of the NPC problem. So it's telling you ahead of time what it's going to do. And you can actually see that the hands, like this again, all of this motion is being entirely driven by just where do the hands need to be? Well, the hands need to be on the ground, so it must squat down. Now the hands need to be up, so it must stand up. It knows to expect the weight of the object, so it actually shifts the robot's center of mass backwards to compensate for that. And that shift happens before it encounters the object, because all of this is happening within the context of a predictive control. And then finally, we wondered if we could take this control and apply it back to walking, sort of our favorite canonical problem. So what if we could get rid of offline trajectories? So no trajectory optimization offline, no animation. Just tell the robot, pick up your feet, put it down, don't fall over. And the result is, I think it's pretty good. So this is Atlas walking outside. It's a relatively natural walk. All of the kinematic coordination comes out of NPC. The fact that the arms swing is an emergent behavior coming directly from the fact that we're regulating angular momentum. I'm showing you in the inset what the robot is planning to do in the future. So that's the live NPC solution rendered from the controller data. As you can see, we're planning a couple of steps into the future, which is a pretty good distance. And we're sort of constantly optimizing every part of the robot's motion to actually achieve this walking. A really neat result that came out of this, I'm going to play it again, it's a good video. A really neat result that came out of this is that if we look at the expected force profiles for a human walking, so there's this characteristic double hump in the vertical force, so how hard the robot is pushing on the ground against the ground during a stance. If we analyze the results from Atlas, we actually get a very similar behavior. And again, this is an entirely emergent behavior from NPC. So it's creating a ground reaction force profile that is very close to what you expect from a human in X, Y, and Z, entirely as a result of trying to do things like regulate the center of mass, regulate angular momentum. We're providing no encouragement for it to do this. Our nominal force is just balanced gravity at all times. So this is just coming out of sort of the natural dynamics of being a roughly human-shaped, roughly bipedal thing. Would you have a little spike in force right at touchdown, which you don't expect from a human? And that's because hydraulics are hard and the legs are kind of heavy. But I think we're pretty close. All right, thank you for your attention. I'm going to end with a few exciting clips of Atlas doing parkour. If you would like to know more, I'm happy to answer questions as much as I can. If you want to know everything there is to know about Atlas, you should come work for us. We are always hiring interesting people. I've got our career site there. We also have some good blog posts if you need to learn a little bit more about how Atlas works. Thank you.
questions?
Thanks for my in the perception, how much information is pre-learning? Is it just random index is possible, or and how many drops is there?
Yeah, so right. So the question is sort of how much did we tell the robot in the perception example about the environment? We've done a little bit of both. So we can do things like generalized Ninja Warrior, any number of boxes that you want to run over, we can just point the robot at them and for the case of the video, we had an exact video we planned to film. And so yeah, we did put some information of this layout of the boxes into the program. So not the exact positions, but sort of generally what sets of primitives to expect. And that's really a practical thing. I mean, if we have a film crew in trying to film a video, we want to remove any chances for things to go wrong. We really don't want the robot to improvise in that case. So we're interested in generalized parkour, but when we're trying to film a single video, yeah, we will tell the system more about what to expect.
You mentioned the walking, but obviously naturally it's hard. How about the heel?
That's yeah. Yeah, so the question is the heel to toe walking an emergent behavior? No, we told it to use heel flat toe. So the mode sequence is specified.
Yeah, and so earlier you showed the demo of I was lifting the so how are you able to predict like the force used on that barbell from only point
by knowing the mass of the barbell.
Oh, so
yeah.
you did know the mass.
We know the mass, yes. Yeah, so I think a really interesting problem is taking vision data and training a model that could estimate that mass. That's not what you're seeing. We told it to expect a 25.
Okay, thank you.
As a smaller model, use to make more effective more big. Good. You're still using the display system.
Yeah.
Last part was very grounded version for it.
Right. Yeah. So the question is, right, are we considering a more interesting and articulated foot behavior? It's definitely something we're thinking about. The flat foot makes my life as a controls engineer easier in some ways. There's only one link that has to make contact with the world. But yeah, it absolutely does limit the set of things that you can do that are sort of perfectly natural. Our toe off control, I think, suffers from having a perfectly flat foot. It's hard for a human to walk in like ski boots, partly because the sole is perfectly flat, so your toe can't flex. Yeah, so it's a very cool problem. It's something we are thinking about. Right, so do we know the geometry, like the exact dimensions of the geometric pyramid? I don't know the answer to that off the top of my head. I would have to ask the perception team. Yeah, sorry. I think we have operated in modes where we expect a box of a given dimension. We operated in modes where we fit a plane surface and just infer from the size of the whole planar region of the point cloud. I don't know which version of that you're seeing in the video. Sorry.
Last question.
I have one question about atlas dancing. So when the human is dancing, there is a relative rotation between the foot and the ground. But if we notice, like the atlas is dancing, the foot is fixed on the ground. Is there any particular reason that it didn't like duplicate or replicate that motion on atlas?
Yeah. So the question is why don't we produce sort of all of the interesting relative motion of the foot to the ground that a human does? And there's rolling, there's toe contact, sliding, twisting, because they're hard and I don't know how to do it. That's the real answer. We have tried some work on things like extended balancing the toes, and it's proven to be very difficult to do it in hardware. I think that as you start doing more interesting contact between the robot and the world, so moving the foot around more, things like the compliance of the surface underneath the robot become a lot more important. And you really, so, if you're balancing on your toes on a 1-inch squishy rubber mat, it's different than balancing on your toes on a hard surface. And quantifying that difference is very helpful. yeah, I would love to do all of those things, but they're hard.
Thank you.
Okay,